This method we discussed. These are some formulas. By inspection, how we can convert an expression into an exact expression, like d of this or d of this. If it comes in a differential equation, then we can readily integrate it, and this expression comes as a result. So these are the formulas you need to commit to the memory, or you can derive also by directly that product rule of derivative or division rule of derivative. And derive all the formula. You check at home how the proofs of all this. So we are discussing solution of first order and first degree ordinary differential equations by integrating factors. Rule 1 is by inspection. These are some examples. Then in rule 2 we have if mdx plus ndy equal to 0, this differential equation is homogeneous and the left hand side is non-zero, then reciprocal of the left hand side is an integrating factor. Integrating factor means if we multiply when the given equation is not exact, then we need to find an integrating factor. If this becomes an integrating factor, then if we multiply our given equation by this factor, then it becomes exact, although the original given equation was not exact. Still joining. And what is the meaning of homogeneous equation? Homogeneous means both m and n are of same degree in x and y. And m and n both are of same degree in x and y, we say that it's homogeneous. So whenever a differential equation is given to us, first we check if it is exact or not. If it is exact, then we apply yesterday's method. If it is not exact, then next we check for the next easier thing, which is if it is possible to solve it by inspection. Suppose you cannot solve it by inspection, cannot make it exact by inspection, then we may go to this route. Then we see if this given equation is homogeneous. Homogeneous means if homogeneous means if m and n both are of same degree in x and y. Let us see an example. Here is one example. So this is given to you to solve. So first you will check if it is exact or not. In fact, you will see that this equation is not exact. Exactness condition we know del m del y equal to del m del x. In here this condition will not be satisfied, so we need to go for some other methods. And also we can see that by inspection also it may not be possible to put it into a convenient form. That is, we cannot make it exact by those formulas we had listed earlier. So here we have to go for next method. So next what we know till now is that if it is homogeneous, you can see that here m and n both are homogeneous. Homogeneous means if m and n are of same degree. Here degree of m is power of x is 2, y is 1, so together 3. Here also 3, here also 3, here also 3. So M and N both are of same degree. Therefore, it is homogeneous and left hand side is obviously non-zero. Therefore, we can apply this rule. So it is homogeneous clearly, and also mx plus ny is equal to x square y square, which cannot be 0, because if this is 0, then x and y, or either x or y, must be 0. But dependent or independent variable cannot be entirely 0. Then the differential equation does not make sense. So therefore, this is non-zero. So reciprocal of mx plus ny comes an integrating factor. Okay, reciprocal of this of mx plus ny, which is 1 by x square y square, becomes an integrating factor. Our job is original equation is not exact. We want to solve it, so we want to convert it into an exact equation. So we multiply our given equation by this integrating factor. That's why the name integrating factor. We multiply the given equation by this factor. Then we have this expression. We multiply by 1 by x square y square. Then you can see we have original equation 1 reduces to this equation. Now if you check the condition for exactness, you will see that that condition is satisfied now. Therefore, this becomes exact. You will check all this calculation here. I have written shortly, and then while you solve, you have to show these steps. That originally the equation is not exact. Therefore, we are going for other methods. Now it is homogeneous, and mx plus ny is non-zero. Therefore, integrating factor is this. Now we multiply the given equation by the integrating factor. Then we arrive at this equation, and now we apply that test for exactness, and we see that the test is satisfied. Since it is satisfied, we can write the solution directly, like earlier, that we integrate m by treating y constant, plus we integrate those terms of n which do not contain x. So the term is 3 by y equated to an arbitrary constant. So we arrive at this result. Alright, so this is the second rule. Second rule is this. When it is homogeneous, mx plus ny is homogeneous, then this becomes an integrating factor. That is rule 2. Now rule 3 is if mx mdx plus ndy equal to 0 is of the form a function of xy into y dx plus a function of xy into x dy equal to 0, then the integrating factor is 1 by mx minus ny. So it all depends on the form of the given equation. You have to observe carefully which category the given equation belongs to. Then based on that, we determine its category and apply the appropriate technique. So here is this example. The given equation is y into 1 plus xy dx plus x into 1 minus xy dy equal to 0. Here again, first we will check for the easiest thing. Easiest thing is that which we discussed initially, if it is exact or not. You will see that this equation is not exact. Since this is not exact, you go for the next easiest thing, which is by inspection. By inspection, if you can solve, that is fine. If you cannot solve by inspection, you have to check what that last method. Last method was if it was homogeneous. But here you will see all the terms are not homogeneous, because here you have power of multiply by y, you will see that first expression is of power 1, second expression is of power 1, 2, 3. That's why it is not homogeneous. Last method, immediate last method we can apply when it is homogeneous. So since this equation is not homogeneous, we cannot apply that. So in such cases, we look out for other things. So it belongs to this category. You see here, y multiplied by a function of xy. X and y as product is present. So it's a function of xy into dx. So it is of this form, plus x multiplied by a function of xy. It's 1 minus xy. This is a function of xy into dy. So it belongs to this category. So rule 3 will be applicable. And also mx minus ny again is equal to 2x square y square, which cannot be 0, because otherwise either x or y must be equal to 0, but the dependent or independent variable cannot be the 0 variable, because then the equation will not make any sense. Therefore, in this case, integrating factor is 1 by mx minus ny. This 1 by 2x square y square. So original equation was not exact, but if we multiply by the integrating factor, then it becomes xx. So we multiply equation 1 by this factor, and we arrive at this equation. After that, you will test for its exactness. Also, you can check in your pen and paper whether it is exact or not. You will see that it is exact. So therefore, we can write the solution as earlier. Is it okay, this much? If you have any doubts, you can ask questions. If there is no question, so we go to rule 4. Rule 4 is that if this expression is a function of x alone, f of x, a function of x only, then e to the power fx dx is an integrating factor. Yes, this equation again is not exact directly. We have to make it exact. Next thing is by inspection. By inspection, if you can, you solve. It may not be very easy to convert it into exact form by inspection. The next thing you check for homogeneity. This is not homogeneous because power of y is 2 and x is of power 1. So it is not homogeneous. Also, it does not belong to this previous category either. In previous category, you need a function of xy. But here, this is a function of xy, but it is not multiplied with x. And here you don't have a function of xy, so previous method is also not applicable. Then next thing we know is that we have to check for this expression. If this expression is a function of x, then e to the power integration fx dx is the integrating factor. So all the previously known methods are not applicable here. That's why we check for this expression. What is this? This expression after simplification becomes this 1 by x. 1 by x, which is a function of x alone. You do all the calculations at home. There may be some mistakes also. So that book also you follow. Pritam had shared that book I recommended yesterday. In that book, you will find lots of problems of this type. The one book I also shared. So all these calculations you check at home. Say that this, suppose that this is correct. So if it is a function of x alone, if this expression is a function of x alone, 1 by x, then our integrating factor is e to the power fx dx. In this case, it becomes x only, e to the power of x equal to x. So the role of integrating factor is to make the original equation exact. Original equation is not initially exact, but if we can find an integrating factor, we can always make it exact and solve it. Here, by this method, we have got x as an integrating factor, so we multiply the entire equation by x, and it becomes exact. So this exactness step you have to show. I have not written here. You have to show that this equation is exact. Del m del y equal to del m del x. Condition is satisfied. So this is exact. Therefore, solution is this. Next, we have rule 5. It is similar to that previous rule. Just slight difference. If all the previous methods are not applicable, not homogeneous, no, we cannot solve by inspection, and the given equation, original given equation is not exact, then if all the previous methods fail, then you can go for this method. Rule 5. Rule 5 says that you have to look out for this expression. This expression is a function of y alone. F of y, then e to the power integration fy dy is an integrating factor. Here you can see this is the equation mdx plus mdy type, and the previous methods are not applicable. Clearly it is not homogeneous. So we look for this expression. This expression is this minus 4m by y. 1 by m of this becomes minus 4 by y. And I am telling you, do the calculations by yourself, check if all of them are correct. So this becomes a function of y alone. No x is involved. So our integrating factor is e to the power integration this f e to the power fy dy, which here becomes 1 by y to the power 4. So once we have got the integrating factor, we multiply the original equation by the integrating factor, and then it becomes exact. This exactness step you will show. Here you will show that the equation is actually exact. Therefore, you can write the solution like earlier. Okay. Next, we have another type of equation called Leibniz linear equation. What is this? A first order ordinary differential equation is called Leibniz's linear equation if it can be written in the form dy dx plus py equal to q, where capital P and capital Q are constants or functions of x alone. X alone means y should not be involved. The working rule is this. Let us see this example. It is an equation is given to us. Here you see trigonometric functions are available in m and n. So this previous methods may not be applicable. You can check first whether it is exact or not. If it is exact, then easily you will get the solution, but more often than not, you will find that it is not exact or previous methods are not applicable. That's why several methods are there. We start with the initial one or the easiest one. If easiest one is not applicable, then we go to the next. If next one is not applicable, we go to the other one like this. So if you want to solve this equation, you will see that previous methods are not that much applicable, so we need a new method. So this Leibniz's equation may be helpful. Let us see if we can put it into Leibniz form. Leibniz form is this. If we can put an equation in this form, then it is called Leibniz's linear equation, and we have a ready-made working rule for this. We want to put it into this form: dy dx equal to py plus q. Given equation is this. Let us rearrange it into this form. So dy dx, after rearrangement, we get this expression: dy dx equal to py equal to q. And p and q, here p is 10x plus 1 by x, which is a function of x alone. And on the right hand side, we have q, capital Q. Capital Q is also a function of x alone, which is sec x divided by x. So we have been able to put the given equation in this form: dy dx plus py equal to q, where p, q are either constants or functions of x alone. These are functions of x alone. It is a Leibniz's linear equation. So if it is Leibniz linear equation, then directly we can write which is the integrating factor. The integrating factor will be e to the power p dx. And the role of integrating factor is that it helps us to reduce the given equation into exact form. So the given equation will be very often not exact, but we can always find an integrating factor by several methods. This is another way of finding the integrating factor. If it is Leibniz's linear equation, then e to the power p dx will always be the integrating factor. In this case, the required solution that you should commit to memory, that it will be y into integrating factor equal to integration of q into integrating factor x plus c. So since this is a Leibniz linear equation, the integrating factor will be e to the power p dx. P is 10x plus 1 by x. This is p dx. So after integration, we see that the expression is x sec x. This is the integrating factor. Therefore, now our solution is matching with this formula: y into integrating factor equal to integration of q into q is sec x by x multiplied by integrating factors. So x get cancelled, you have sec square x dx plus c. So after integrating, you get the result. It is very easy method. Just you need to show that the given equation is linear first order, and we can put it into this form, and readily we can obtain the solution. Another example you see here, it is given. This equation also we can put it into Leibniz linear form, but in a slightly different way. In previous example, we had written dy dx. Here it will be Leibniz linear equation. We consider x as dependent variable and y as independent variable. If we want to write dy dx, then it becomes y divided by this, which we cannot put into Leibniz's linear form. So if we, instead of writing dy dx, if we write dx dy, then you see dx dy equal to px plus q. So it is in that Leibniz linear form, dx dy equal to p. Here p is a function of x alone. P and q both are functions of x alone. In this case, we are treating x as the dependent variable and y as the independent variable. Therefore, our integrating factor is e to the power p dy is this p dy, which is 1 by y. Therefore, the required solution by that formula we can write this. This is Leibniz's linear equation. Today we will discuss just one more thing, which is called Bernoulli's equation. Bernoulli's equation is this. So if we take online classes, it saves my writing. It becomes easier for me. For you, understanding or taking feedback, those things are difficult, but I am saved from writing all these things. So next is Bernoulli's equation. Bernoulli's equation is an equation of the form dy dx plus py. Leibniz equation was dy dx plus py equal to q. Bernoulli's equation has an extra factor, which is dy dx plus py equal to q into y to the power n. This is the extra factor. If this is present, then it is called Bernoulli's equation, where p and q are constants or functions of y alone, of x alone. This x, y is not involved, and n not equal to 0 or 1. It's called Bernoulli's ordinary differential equation. So how do we solve this Bernoulli's equation? To solve it, we divide both sides by y to the power n, so that this equation becomes y to the power minus n dy dx plus p into y to the power 1 minus n equal to q. Then we put y to the power n minus 1 equal to a new variable z. We assume that this is z, so that now if we differentiate this and put these values here, this equation 2 reduces to 1 minus n into y to the power minus n dy dx equal to dz dx. Differentiating this, we get this. So equation 2 now reduces to, if we use this value, equation 2 reduces to this expression. And this expression, after simplification, reduces to this expression, which is dz dx plus 1 minus n into pz equal to q into 1 minus n. Here, since n is a positive integer, this is a constant. Therefore, this actually has become now Leibniz's linear equation. It was Leibniz's linear equation. It was of the form dy dx plus ey equal to q. Here you see it is exactly of that form. In place of y, the variable is z now. So dz dx plus p into a function of z alone equal to q. Okay. So not
so
function of z, function of x. Yeah, tell which one.
So this one, when we put y to the power 1 minus n equals to z, after that, how that equal to this equation? 1 minus n into y dy by dx equals to dz by dy.
Yeah, we are differentiating this expression with respect to x. Okay. We differentiate this with respect to x. 1 minus n will come here into y to the power 1 minus n minus 1. So plus 1 minus 1 gets cancelled. What remains? Y to the power minus 1. And we are differentiating with respect to x. So you will have a dy dx here.
Yes.
Okay. And in the right hand side, you have dz dx.
Okay.
So this just differentiating both sides with respect to x. N is the power which comes here, n into y to the power 1 minus n minus 1. Okay, so this expression we get by differentiating both sides of this with respect to x. Now we use this expression here. Means dy dx, you replace the value of dy dx from here. Then equation 2 becomes like this. Okay, you do it in pen and paper. Take this dy dx, this value, it will be y to the power n divided by this into dz dx. Put it here, simplify, you will have this expression. This expression further we can put it into this form, which is Leibniz linear equation of the form dz dx plus ez equal to q. Yes, this is Leibniz linear equation, so like earlier method we can solve it. Let us see an example. So we want to solve this equation. This equation does not look like any of the previous one. We divide by x into x into y to the power 6. Then we have this y to the power minus 6 dy dx plus y to the power minus 5 by x equal to x square. So this looks like which form? Next, what we have done, we have put y to the power minus 5 equal to z, so that we get this expression. Then equation 1 has become like this, which is Leibniz's linear equation. If it is Leibniz's linear equation, then we can see the integrating factor is this, and then we can get the solution. See carefully the method of solution for this. Why we have multiplied by x into y to the power 6. Because first we need to put it in Bernoulli's equation form. If it is of Bernoulli's equation, then we can convert it into Leibniz's equation. Bernoulli's equation is of this form: dy dx plus py equal to q into y to the power n. But this equation is not exactly of this form. So we have divided by x into y to the power 6, so that that we can put into Leibniz's linear equation.
So your audio is not coming. Can't hear you, sir.
What did you tell?
Cannot hear you clearly, sir.
Okay. Okay, in this equation, so general equation is not in Bernoulli's form. Therefore, we have multiplied by x into y to the power 6, so that we get rid of this y to the power 6 in the right hand side. So after dividing by x into y to the power 6, we have this expression, y to the power 6 comes here, and in the right hand side we have simply x square. We got rid of y. After that we have put y to the power minus 5 equal to another variable z. So we have differentiated both sides of this with respect to x, and we arrive at this expression. Now we have used the value of dx, dy dx in this equation, so it reduces to this form. And this form is again can be simplified in this manner, put it in Leibniz linear form. So if it is in Leibniz equation, then we know what is the integrating factor e to the power ex. So we have got the integrating factor as e to x to the power minus 5. Therefore, we have got the solution. Okay. Let us see another example. We want to solve this. Here we have multiplied by xy. We multiply by, so you not multiply, we divide by xy. So that you have to check from the given equation that what should be our first step, whether we should multiply by some variable or constant, or we should divide by certain variables to put it into a convenient form. Here, if we divide both sides of the equation by xy, then we have this expression 1 by y dy dx plus 1 by x log y equal to e to the power x. So again here if we put log y equal to another variable z, then we have this step. So this value of dy dx, if you put in equation 1, it becomes like this, which is again Leibniz's linear equation. And once you know that it is Leibniz linear equation, then there is no problem. You can find the integrating factor and write the solution like earlier. So these things will be easier by practice. One, you do these things today at home in pen and paper, and in that book you will find several problems. I will also provide you tomorrow the problem set of this unit, where you will find more problems. Once you solve a couple of more problems, you will be able to see that which technique is applicable and what should be your first step in case it is Leibniz's linear equation or Bernoulli's equation. Then how to convert from Bernoulli to Leibniz. So here is the step, means there is no fixed rule by which variable you should multiply or divide in the first step. The next steps are similar. This will be all for today. You tell if you have any question. Any question?
No, sir.
Okay, then you practice more problems based on this. In that book, you will find many problems. You try to solve some based on the rules, try to apply, understand the rules and apply them. Okay, that will be all for today. Let me take the attendance. For that you can leave. So there is Abhijit, Adarsh, Aditya, Anjali, Anku, Arnab, Baharul, Vikiran, Rajnandan, Devangshi, Farhanul, Govind, Manshu, Inamul, Jatin, Kapildev, Manash, Manish, Manthan, Padmanav, Prakash, Pritam, Rahul, Raj, Adarshi, Rakesh Kumar, Sanghamitra, Ronak, Anton, Shivam, Roham, Sagar, Gaurav Datta, Saurav Das, Neil Sharma, Tama, Tamalika, Tapas. Okay, have taken the attendance. You can leave. Thank you all.
Thank you, sir.
Thank you, sir.
Thank you, sir. Thank you, sir.
Thank you, sir.
Thank you, sir.